And let's welcome you.
Yeah, thanks for the introduction. Thanks for having me here. So I guess this is the talk about extrapolation of nonlinear models. I guess I check out the other talks in this workshop, and surprisingly, I think it's pretty diverse. I feel like my talk is pretty theoretic and very narrowly focused on domain adaptation, and pretty theoretic and very toy settings. But this is something that I've been thinking for quite a while, especially around the time that oh, I see. Yeah, that makes sense. Thanks. So yeah, so I guess I think the starting point was something that I spent a lot of time thinking about deep reinforcement learning theory. So like and then when you think about the reinforcement learning, and when you have nonlinear models, you use the nonlinear models for policy, for model dynamics, for the value function, so on and so forth. And this extrapolation of the model matters a lot. And I think 2 or 3 years ago, I probably still true right now. I think most of the deep reinforcement learning theory paper are kind of like using linear models in one way or the other for the extrapolation. At the end of the day, there's something linear in there. And I was thinking whether we can have some nonlinear extrapolation to new domains. And that's kind of the motivation for some of this. But anyway, okay, so I guess I probably don't have to say domain shift is ubiquitous. And there are many different settings which I'm not going to talk about. There are supervised domain adaptation, unsupervised domain adaptation, and now in this foundation model era, there's also this unsupervised pre-training, and then you adapt the models to new downstream tasks with supervised domain, supervised kind of set adaptations, or like a zero-shot, multi-shot, few-shot adaptations. But these are not the settings I'm going to talk about. I'm talking about this very, very plain setting. I call it, just for the purpose of this talk, zero-shot vanilla setting without any nothing. Like just basically you have the true and test set has the same target function f, literally exactly the same target function f, and you train on distribution p, and then you test directly on distribution q without having any other information, no labels on the downstream tasks, nothing. So, or in the second part of the talk, I'm going to talk about how do you extrapolate to the whole domain in the worst case sense, right? You have a L infinity recovery. So basically this is all about, the similarity between P and Q, right? Because if they are not similar, there's no chance you can extrapolate. And also about the structure of the model class. If the model class is just almighty and contains all the possible functions, there's no chance you can extrapolate. Actually, you'll see like even two-layer networks is probably too expressive. So we have to restrict a lot the similarity between P and Q and the model class. So I guess so just set up some notations. So the function class, let's call it F, capital F, and let's say the ground truth function is called G, and let's assume G is in F. Everything is the simplest possible, and the learned function is called F. And basically the question is, what conditions on the target function P and Q and the function class F can ensure that for every function F and G, if you get a small error on Q, small error on P, right? For example, you are training on P, right? You get the L2 error guarantees on P, and you want to make sure that that actually translates to L2 guarantee on distribution Q. And here the P norm is just the average error on P and Q. Yes. Yeah. So I call it average error ratio just to give a name in the paper so that you can refer to it. But it's nothing else just beyond just you take the ratio and you restrict the function f and g to be in function class capital F. And this is the analog of the h delta h distance for regression. And I think we want to work for regression because for classification, at least, it's just it's too hard. Like the regressions, you have some structure.
For regression, actually, same as it can be called the discrepancy.
Yeah, the IPM.
So it would be a difference as opposed to taking the ratio. And the ratio might actually be somewhat tricky, but maybe you're going to talk about it.
Yeah, so I think
so that would be exactly anyhow.
I think I do, yes, I agree. So I think I do somehow I think we did want to use the ratio as opposed to the distance, because I feel like this is a little bit probably I would say it's probably a bit more a little bit kind of easier to bound when you have a regression, because when you have the absolute distance, for regression, how do you interpret that? Anyway, so I guess we're working with the ratio.
Questions like in that respect, but whenever you have a ratio, you have to worry about the denominator.
Yes. Yeah. That's true, but I think even you have this absolute distance, it's kind of hard to. Anyway, so let's work with the ratio just for a moment.
Estimating the distance. What Linear is saying that you cannot estimate the ratio, you can estimate the difference.
Unless you have a lower bound.
Unless you have a lower bound on the denominator.
Quick thing.
Okay.
I don't think he's trying to estimate anything, right? He's just saying that if
this is my definition of the problem.
You're not trying to estimate it, you just assume it.
Yeah.
Okay.
I'm trying to bound it. Yes, I'm trying to bound this. Yeah. So and I think intention is that maybe sometimes you get a very small error on P, but you can allow polynomial blow up on Q, right? So for example, your error on P is like 1 over d to the 10, and then your error on Q could be 1 over d to the square. D square, that's acceptable, even though the distance, the absolute, the difference is not that big. Yeah.
I guess one simple question: why superveloc pairs?
In
some sense, I thought you made the assumption that the optimal f is the same for both P and Q.
Yes.
So why not just super with respect to the optimal?
Oh, if you believe that G0 is in it, then if you believe it's kind of like a subspace in the function class is like a. Are you saying like why just don't have one function f?
Yeah, and G is just the G star in f.
I guess the confusion is you mentioned that G is the ground truth.
Sure. Yeah, I'm. Yeah, G is the ground. Just to give you a sense on what G means here. None of this matters that much. I think just even you have like let's say no G, it's the same. It's almost the same question. Like it's still pretty. Like the difficulty doesn't change as much. Anyway, yeah. So
linear class, it doesn't matter.
Yeah, sure. Yes. But we want to do nonlinear class. But sorry. But it's nonlinear in the parameter space. But it's still linear. It's still a linear function, linear subspace in the function space. Yeah. Anyway, so cool. It's just I don't want to assume 0 is in the function class sometimes. I think that's the only reason why we have the subtraction. Anyway, so and for the prior works for linear models, I guess you can just actually this is the equality, and then you can bound this by something like about the spectrums, the differences of the two covariance matrices, right? So basically, you say if Q is bounded by P in terms of the covariances, then you can control this. And know that this doesn't really mean that Q has to be a subset of P, the support of Q has to be a subset of support of P, right? The support can have no overlap, but the covariances can have overlap or coverage in some sense. And that's the blessing of the linear model that allows you to do that. And for nonlinear models, basically, I think this is probably the best people knew. So you just say, you do the most kind of like the simple thing, and then you say, oh, I'm sorry, I'm not having a typo here. So basically, you have to assume that support of Q is a subset of support of P. Otherwise, there's no extrapolation. Once you go out of the support, it's all bets are off. And that's not the case we want to study. I think for reinforcement learning, for all of these cases, like you do need extrapolations to out of the support extrapolation. And I think for classification, of course, Ben is an expert on this, but I think it's still pretty hard to bound this, right? So. Sorry. Yeah, sorry, my bad. Shai knows much better than me on this, but sorry. But I think it's kind of like in terms of the results, like this linear kind of results, it's still not clear how do you bound the H delta H divergence. So
yeah, in that case, you can actually say things as opposed to taking the. So, but go ahead.
Okay, yeah, maybe we can talk offline. Yes, at least for the multiplicative case, I think I don't know any other results and other than this bounded density ratio versus under the linear model. So basically, we just want to kind of like go beyond the density ratio and for nonlinear models. But it turns out even for two-layer networks, this is almost a trivial result. Don't get surprised by that. It's just you know, if you don't have if the support of Q is not a subset of support of P, and there's some very mild regularity conditions, even you just have a two-layer network. This is two-layer network. You'll get infinity. And the reason is just that you just implement a function that is 0 on the P, and non-zero in the differences between Q and P, and that's it. So basically, this function is just always 0 under P, and in the diff between Q and P, you have a non-zero value, and then you get infinity.
I'm just wondering if there's something a bit disconcerting that your measure is scale invariant. Imagine that your F was a unit ball of some function class. That unit ball constraint would be irrelevant because I found a very bad F that was outside the unit ball and I rescaled it. It would then be in the unit ball and satisfy thing for soup. It somehow feels like the constraint's not active, but I think you have to exclude something around 0 in the denominator. You cannot, I think, ensure this for functions that have very small norm. Linear models are special because they're kind of scale invariant. You can do whatever you want to them. But I think if you just took a kernel class, this will be infinite for any PQ.
Yes, for any PQ that are not that satisfy support of Q, yeah, that doesn't have the density ratio bound.
I think it's a more fundamental problem. I think you have to exclude something in the denominator.
I don't. Maybe I don't know. But at least this one we are not doing. You know, this one is kind of like relative. This is like there is no. It's very generic. Like you can change the statement of the theorem in many ways to still get infinity very easily. Like it's a very robust case.
If the radius of the kernel class grows, you get arbitrarily wiggly functions.
Yes, that's true.
Your ratio is scale invariant. So I will take.
But that's scale invariance, but it's good for this. Right?
We scale it so it's within.
Maybe let's take it offline. Yeah.
Yeah, we can take it offline.
Yeah.
For some issue.
Yeah. Okay. I thought scale invariant is good actually to make it easier to interpret. Anyway, but we can discuss later. So and this is just that you take G to be 0 and you just have a bump function such that I think that I don't even have to go through this. I guess I make it probably too complicated. So just you just take a indicator function, which then you get the soup between the norm, and then it becomes the density ratio. So basically, I think the reason why I want to show this is basically saying that if your function class can implement a bump of spiky function, a bump function, then you are just in the density ratio case, and there's no way to recover from that. So basically, you have to exclude, in some sense, the spike function.
Will be bound the biggest derivative, the biggest soup over the derivative. So I mean, as long as the soup of the derivative is finite, it's not going to be infinite.
Yeah, but I want to make sure that I can work with the case that this is infinite.
Yeah, I understand. But
yeah.
Like.
Okay. So basically, I want to do basically the takeaway is that if you need even more fine-grained structures, right? This is not enough. We need more assumptions on P and Q, and maybe more assumptions on function class F. So this is the case that we can make it work. It's a very special case, just to give you a heads up. So let's say the input is like a k-dimensional, and we assume the joint distribution of X can have arbitrary shift, but the marginal distribution of Xi doesn't have a shift or have a bounded density ratio guarantee. So basically, for each of the coordinates, you do have a bounded density ratio guarantee, but the joint distribution can shift a lot. And I guess some of the examples I came up with, these are just some stories about the potential applications. For example, you can say x2 up to xk are the foreground, and x1 is the background. And the distribution of the background and foreground you don't have a really a shift, but the combination of the background and foreground, you have a shift, right? So maybe there's a different correlation between the foreground and background in the training and test, or maybe temperature and the precipitation. So the correlations between X1 and X2 are different in the source and target distribution, but the marginals of X1 and X2 are you have bounded ratio density guarantees. And I think this is actually one of the original motivation we are thinking about NLP, and you think about, for example, if you have a verb phrase in your training set, some of the verbs associated with the noun more often, right? But the collection of the verbs and collection of the nouns probably don't shift that much, but the combinations shifted. So I think I heard someone is using also this for different scales, right? So for example, you could have like in the training set, you can have like 3 different scales, and their combinations of the scales are not the same as the combination of the scales in the test set. So and there's a very big assumption on the function class, which is because we know that even you assume this, it's not enough. If as long as this is two-layer network, right? Assume only this, is not enough. So you have to assume something about the function class, and we assume that it's really just a decomposable function where each coordinate is went through a nonlinear function, and you sum it up. We also have some extensions where xi doesn't have to be a one-dimensional variable. It could be like a multi-dimensional variable, but still you need to assume that you have this decomposition structure. So this is a strict extension of nonlinear models, but much weaker than two-layer networks. So that's the case that we can prove. Okay, so let's look at a motivating example to just get some sense on what's the mathematical structure here. It's actually relatively simple. So let's only work on the case where there's 2 variables, and the variables can only take discrete values. So in some sense, these are, for example, verbs and nouns. And the function class is f1 of x1 plus f2 of x2. And in some sense, the extrapolation, this is probably the hardest case for extrapolation, or the easiest case. Like I say the best test case for testing whether you have extrapolation. So basically, you just have to determine whether this ratio is infinity. So basically, the question you can ask is whether there exists some function f such that f is just always 0 on p, but f is non-zero on q, right? If this is can happen, then there's no extrapolation under our bounded density, under our like a multiplicative measurement. And if this cannot happen, then it's a good sign, and often you can bound the ratio eventually. So basically in this case, the function is really just a table, right? So you have two. Let's say here I have 6 possible options for x1 and 6 possible options for x2, and this is the distribution for p. And the question is whether we can extrapolate to a distribution q, which probably has a different support. And in this case, I think the main observation is that FAC plus FBD is equals to FBC plus FAD because of the decompositionality. So basically these 2 things add up. The sum of these 2 is equal to sum of these 2. So that's why when a function is 0 on p, it has to be 0 on all the entries. Just because I guess if you have 3 zeros here, and then this will be 0. And for the same reason, everything else will be 0. So and that at least pass the sanity check. And that's how and you can probably also imagine that you can extrapolate even for non-zero values. For example, if you know the values for these 3 things, even though they are not 0, you can determine the value for this one. And then that means you can determine all the values that you haven't seen in the support of P. So everything got extrapolated to the rest of the table. So but in some other cases it's not true, right? So for example, if the support of P is like this, and in this very structured way, then you can have a situation where f1x is like this and f2x is like this, and then when you sum them up, you get zeros in this subtable and these zeros in this sub matrix, and -2 in these 2 cases. So basically you don't know, even you see zeros and zeros here, you don't know what the values here, because the values here could be -2 and 2, it could be 0 and 0, right? Those 2 cases can both happen, and that's when you don't have extrapolation. So and if you think about it, so basically this is a good case and it's a bad case. And in some sense, it's just a pretty trivial rank 2 matrix completion problem, because your assumption assumes that this this table is like you have this decomposition structure. So so that's why the numbers here is just a rank 2 matrix, and it's actually a very special rank 2 matrix. And when you have this rank 2 structure in a table, you are just completing you see the values here. You want to complete the matrix, and whether you can complete it just depends on how what's the spectrum of this matrix. It's more about, from the graph perspective, it's about clusterability, and from the matrix perspective, it's about the eigen the spectrum of the matrix, right? So, and we can just use some of the classical graph theory, but here I guess I'm kind of like depicting the clusterability. So here, if you look at the clusters, defined by this on the support of P, there's a clear separation. It's 2 clusters. That's when it doesn't work. And in this case, everything is connected, so that's why it works. So mathematically, I guess what you can show is that suppose you say Pij is the Chilling distribution, and D1, D2 be the row and column sum of P. So these are the marginals. You can define the Laplacian for this matrix. So the diagonals are the marginals, and the off diagonals are the P and minus P transpose. And you can define the normalized Laplacian just as usual. And then you can prove that, under these assumptions, this ratio tau is bounded by 2 things. One thing is this lambda to the second largest eigenvalue of the normalized Laplacian to the power of -1. So this is basically measuring how far, from rank 2 matrices, my bad, from how far this support of P is from rank 2 matrices. And this is the density ratio for the marginals, which you anyway have to have, because if your marginals, because if one function f1x cannot extrapolate, if you don't have coverage on the marginals, there's no way you can extrapolate at all. So yeah, so this is a pretty simple theorem, and we can also extend this to continuous input settings, where each of these variables are Gaussian, we have experiments with all kind of different settings and find out what we can prove and what we cannot prove. And this is the one case we can prove. So you can prove that the assumptions here is that every pairs of the features are Gaussian, so jointly Gaussian. And you have actually we assume you have matching marginals, which is not entirely necessary if you truncate the support. But if you don't truncate the support, you have to have matching marginals to make sure that a single fi is to extrapolate. It's not very important. Let's just say the marginals, you can extrapolate in 1D sense because you have matching marginals, and also we assume some without loss generality, there's some kind of like the sigma p and sigma q, the covariance are identity, and x's are mean 0. And under these settings, you can prove that the ratio we are trying to bound is bounded by d over the minimum eigenvalue of sigma p. So sigma p is the covariance of x. So so basically, you don't really need that p to be a subset of q. You only need that the covariance of p to be reasonably well dispersed, because the minimum eigenvalue of sigma p is so basically you don't want in any direction you have no coverage at all, right? That's what the minimum sigma p is trying to say. But you don't really need the p to be a subset of the support of p to be a subset of support of q. Yeah, and this theorem does require quite some calculation using some of the spherical harmonics, but nothing. It's really just about you need to find out the right mathematical language to do the calculation, but the core idea is really just what we had before. Yeah, and we also have some extensions where each of the xi's are high dimensional variables, and in that case, I think we can only handle 2 components, x1 and x2, and each x1 and x2 are high dimensional Gaussians, and under some similar conditions, you can prove a similar type of theorem. Yeah, they are in the paper. In that case, we don't know how to extend to 3 variables, just because I think when there are 3 variables, there are some issues with the spherical harmonics tools we are using, and we couldn't figure it out. Yeah, so and I think another thing is that this is somewhat comparable for the bound for linear models, right? So if you assume the models are linear, then recall that we can prove that you have this, the ratio is bounded by this ratio, which is bounded by, if you assume sigma q is identity or something like that, then you only need to, you can bound this by the lambda mean of sigma p inverse. So there's a difference between the numerator. So like the bound is actually d times bigger, but at least qualitatively they are of similar type. So so basically you get the same bound even though the function class is not linear, but with some also additional assumptions here as well. Yeah. Cool. So we have some empirical results, just in case you want to take a quick look. So this is all simulated environments. It's basically a few lines of Python code. So basically you just do simulate the settings we have done, like you have a decomposable function, and you can try two kind of algorithms. One algorithm is you train a structured model. Another algorithm is you train an unstructured model without any constraints on the decomposability. And you train the two models reach the same in-domain validation loss. So basically your P, the loss on P is exactly the same, and you test whether the loss on Q are the same. And what we have seen is that when the in-domain loss is very similar, the OOD loss could be much higher if you don't restrict the function class. So this seems to suggest that indeed restricting the function class could possibly give you better extrapolation power. Of course, in reality, people don't really restrict it that way. I think the reason why in reality you don't have to restrict it is that there are implicit biases that actually prefer certain type of structures, even though your function class is really big, but your training algorithm prefers certain simplistic structure that we don't understand very well. But here we are just making it explicit, and you can still see some gain here in the OOD loss. So, and there are some follow-up works. The paper was published in 2023, which is probably 1.5 years ago, and there are some follow-up works on how to extend this to some other cases, where you have a little more complicated conversationality. For example, you have fx plus gy, where f is much simpler than g, or you have another function on top of the sum of the fi's. Cool. So I guess so that's the first part of my talk. Let me check on how much time I have. Yes. So the second part of the talk, if maybe I'll take some questions just before I move on.
This is super cool. So if you go back to what you just said about the implicit bias,
yeah.
Would you expect that the models tend to learn and have an implicit bias towards the function class that you described?
I don't think the training algorithm doesn't know what the ground truth functions are, right? So there's some implicit bias by the training algorithm, which may or may not be the function class I assume. Probably most likely it's not the same biases as the function class I assume, which is pretty arbitrary, right? But there may be some correlation, right? So you bias towards certain kind of simple function class, and it correlates with the this kind of a structure. That's possible. Yeah. But generally empirically, I have no evidence at all. I don't believe that this is the right function class. This is more like we're just trying to do something beyond linear models. So I guess if there's no any other questions, I'm going to move on to the second part of the talk, which is another paper where we try to deal with the L infinity recovery, which means that you train on P and you test on the whole domain. Of course, the domain needs to be compact and bounded. So, but you want to make sure that you extrapolate to every point in that domain.
Generalized linear models, you feel like that's beyond linear models?
Sure. Yeah. Yeah.
Because there is also
this is not exactly the same as the generalized linear model, because you do have these are very nonlinear.
So just trying to see whether you know this other work where they have similar results, but for exponential families, where everything is expressed in the ratio of teacher information. It seems very similar in some sense, right?
Oh, so you are saying like there are results in for generalized linear models with similar things. I think so. I guess, yeah. Yeah, maybe this is my biases, but I feel like generalized linear models is not very far from linear models because you can still reuse many of the tools. It's convex. Like you have the linearity. I don't know this. Arguably, like at least I'm trying to find some more tools to deal with nonlinear cases that are somewhat different from the tools we have used before.
And what is the general motivation for this additive structure?
For the additive structure, not really. I think it's just we start from something simple. Yeah. So okay, so the second part, right? So I'm going to talk about L infinity recovery or worst case errors. So and why you care about worst case errors? I think this relates to some of my original motivation when I read some of these papers on bandits, RL. When every time you involve a network in bandits and RL, and you involve the network in this physically informed networks where actually you do care a lot about L infinity error because you are simulating some physical process or simulating some physical equations, and also adversarial robustness. So and in all these cases you care about L infinity recovery. So and also I don't see any other workaround, at least. So it sounds like you just have to care about L infinity recovery. So so that's why in this paper we studied this case where you have a bounded domain D and you have a ground truth function F. Sorry, I changed the ground truth F to G to F. Anyway, but you have a function F and you want to learn the function G, which is pointwise close to F on the domain D, and you have some epsilon error, which is the L infinity error. So some of the existing results. So for linear models, I think that L infinity recovery is at least qualitatively similar to L2 recovery because you can bound the L infinity error by the L2 error by this by some of the covariance matrix inverse and the size of the domain, so on and so forth. And if you have neural is finite width, I think you can say that if you recover, because neural is finite width in many cases is identifiable. Like you can, in theory, identify all the parameters exactly, and then you can do the L infinity recovery. So I think that's one type of approach to get L infinity recovery. You just exactly recover all the parameters, and then you get L infinity recovery. So and that's pretty much the only results I know about neural networks L infinity recovery. Like you have to go through the parameters. So basically, what I wanted to have is I want to have a result which we don't have to go through the parameters, where you can recover without this kind of strong situations. And when you have two linear networks with infinite width, then you cannot really recover all the parameters, even you are given infinite compute. And I think we have proved something like, L infinite recovery requires exponential D samples, which is probably not very surprising. And the reason is really just that similarly to before, so even with you don't have a bias, as long as you have infinite width, two-layer networks can represent spiky functions, and the spike cannot be identified using polynomial samples, right? If you just have a function which is almost zero in all cases and only non-zero in an inverse exponential small region, and there's no way you can recover that with polynomial samples because the chance you can hit that region with the spike is just the inverse exponentially small, and you need exponential number of samples to hit that region. And for RKHS, I think partly because it's kind of like it's only possible when the eigenvalues for the kernel decays very fast. And I think the reason is the same thing, right? So the eigenfunctions of the kernel are often very spiky. So so basically, if you have RBF kernel, which is the standard Gaussian kernel, I think the L infinity recovery does require super polynomial samples because you just compute the norm of the you plug in the norm of the bound. You compute in some sense you just compute what's the L infinity versus L2 ratio in that function class. If that ratio can be infinity, then you cannot recover. Otherwise, you can recover. So something like that. So and I think basically the conundrum here is that in my opinion, the real fundamental issue is that most reasonable nonlinear function class contains the spiky functions, the RKHS, the neural networks with infinite width, so on and so forth. So and spiky functions just seems to be fundamentally hard to learn with L infinity error because you don't know where the spikes are. So and the idea we had again, it's only a small steps towards something, hopefully something bigger. But so we think that random functions are likely to be not specky. So, but of course, the tricky thing is how do you define a random, right? So we assume the ground truth is random, but how do you define a random function is the most tricky thing here. So and the main result we have is that you assume the ground truth f is drawn from some Gaussian random field, a Gaussian process, and of course the Gaussian process, the kernel needs to have some decay of the spectrum, and then in this setting you can prove that the L infinity to L2 ratio is much better than the worst case when you assume the randomness. And then you can prove that the L infinity recovery is no harder than L2 recovery up to polynomial factors. So yeah, that's pretty much the main result. And let me just probably spend like 1 or 2 minutes to just define some of the basics for spherical harmonics, which is the tools that we're going to use. And that's actually it's useful to define them to even state the theorems in a formal way. So basically you have a domain, which is the sphere, and you have some inner product kernel K, which is a one-dimensional function on the inner product of X and Y. And we know that in spherical harmonics are the eigenfunctions of any inner product kernels. All the inner product kernel has the same eigenfunctions, which are this kind of spherical harmonics. And spherical harmonics can be grouped into groups, right? So based on orders, right? Y1D is the group of order 1 spherical harmonics in dimension D. Y2D is the group of order 2 eigenfunctions, and each of this group is actually a subspace of eigenfunctions because they have the same eigenvalue. So that's why you have a subspace of eigenfunctions with the same eigenvalue. So basically, the kernel applied on H is just a constant function times H for all the functions H in each of this group, and the dimension of each of this space is this nkd, which is something about d to the k or k to the d, whichever is bigger. So all of these are kind of well known in spherical harmonics. Okay, sounds good. Yep. So oh, I see. So and the projection operator pi k is the projection operator to the space ykd. Yeah. So so the basic thing is just that because all of these are projections, and this is the union of all the space is the product of all the space is the whole space. So you can decompose F into this infinite series by projecting it to different part of the space. This is kind of like you turn it into the frequency space. In some sense, this is like the Fourier coefficients in some sense. So and the problem with this is with it is that fundamentally is that for function h in this ykd, the infinity to 2 ratio is going to grow exponentially fast as k goes to infinity, because this nkd is something d to the k. So you're going to have more and more specky functions when you are going to the lower order. So it just becomes too specky eventually. And what we can prove is that if you draw the function g uniformly random from this ykd, then the ratio becomes d times square root log k, as opposed to nkd, which is exponential in k and d, and now it's polynomial in d and actually log in k. So basically the random functions are much less specky, and in comparison, as I said, this is the ratio is much bigger, and this is like some mathematicians in spherical harmonics, they prove this for low dimensional case. Basically they didn't prove the constant here for the dependency on d and k. They just assume d and k are constant, and we basically identify the exact dependencies. And one of the nice thing about it is that we do use a new proof, which is much simpler, like half-page proof, compared to like the original problem, like a 15 pages proof. It's just some kind of simple calculation with using concentration inequalities.
The statement you made on RHS is the two norm there. Yeah, the two norm there, is that the norm within the RHS, or
I haven't wait.
L infinity over L2 for RHS is right there.
Yes. Yeah.
It's only possible when,
Yes.
yeah, values of the kernel decays. Are you, because this cannot be a statement about all RHSs if Is two, what is the two norm for you here? Is that the norm within the RKHS?
Finally you care about the norm in where the two norm? Did I mention two norm?
I mean, you're comparing L infinity norm to.
I'll talk about RKHS maybe. Just give me 1 minute. I think probably I'll have a better slides to answer this question. Just very, very quickly, yeah.
We have like less than a minute.
Sure. Yeah.
Maybe you can break.
Yeah. So maybe I'll just wrap up this slide and then I have just 2 more slides. Yeah. So right. So basically, the way we describe this the way we describe how fast the function decays is by looking at the norm of the projection to each of the subspace of the functions, and this alpha is deciding how fast it decays. And basically, you just say that if the alpha, so basically we prove that if alpha is bigger than 0, so you have some decay, then you can learn it with L infinite error. So and now probably this is the answer to the question. So basically on the above this line, this is the upper bound. So possibility results. So basically, when alpha is bigger than 0, if you assume random f, then you can learn with polynomial time. And if alpha is bigger than 0, bigger than 1, you don't have to assume anything. Just even no randomness, you can prove it. And when alpha is less than 1, you can prove that this requires exponential d-samples for worst case f. And even you assume some bounds on the RKHS kind of norm, which is a different type of assumptions, you still have to, you can only deal with alpha is bigger than half. When alpha is less than half, it's just like you cannot learn by any kernel methods because the RKHS norm is infinity. Does it make sense?
I was just asking, I mean, are you comparing, because if I have the bound on the RKHS norm and my kernel K is bounded, then I immediately have a bound also on the infinity norm.
Yes.
Just by, so that's why I was confused about why you need an eigendecay.
Maybe I think this particular point, I think is sort of like it's sort of let's take it offline. Maybe I also probably have to think about it. Yes.
Okay, fine.
Sorry. Yeah. Okay. Anyway, so these are some kind of comments about neural networks. None of this really solved the neural networks issue problems, because for neural networks it's very hard to define the randomness. So I guess I'll just skip this. I guess just jump to the conclusion. Yeah. Thanks.
I think we're going to take questions offline during the break.
Sure.
Thank you very much. So does the break now 10 minutes? Please come back for a last talk. Okay, 15-minute break.